So let's say we're looking at like light and it's hitting like the top of like just this thin, very thin like glass sheet or whatever. And the question becomes, well, how is this light gonna pass through the glass, right? And if we had air underneath here, well, it's pretty simple. It's just gonna go that like whatever path it was initially going on. So this angle of incidence right here would equal the angle that's being entered out, right? And that's pretty simple. But if this is a different material, light will do something that we call refract, right? It's going to refract, it's going to bend. And if you have, let's say you have like water here, right? Well, with water, what actually ends up happening is the light bends toward the normal, right? And we call this angle the angle of refraction. So the angle of refraction, right, ends up being less than the angle of incidence if light is entering a material that's going to slow it down, make it harder to move. And how much does this material slow down that light? Well, we call that the index of refraction. So the index of refraction is we use n to kind of symbolize that, and it really kind of tells us how much light slows down, or by what factor. I guess not this specifically, this n, but like by what factor does the light slow down or speed up. So the equation, right, for the speed of light in a material is going to equal c over n. So not c times n, c over n. That's why I was a little hesitant on saying like n is the factor at which speed changes, because it's, I guess, the inverse of the factor. Or it's the factor of the inverse. I don't know. Point is, this n is always going to be greater than 1, right? The max speed light can go at is in a vacuum, which is c. And, you know, if you have something less than 1, this speed is going to be greater than the speed of light in a vacuum, which is impossible. So this n tells us, yeah, how, like, I guess, like, how much does light slow down, right? Greater n means greater difference between vacuum speed and the material speed. So if you have something like a vacuum, or something that is allows like, I don't know, if you have air from Venus versus air from Earth, I don't actually know if they're heavier or lighter, but whatever. Point is, if you have a material or a vacuum that's just gonna make light go faster, the angle gets larger, right? You get the light bends away from the normal. So the reason, right, like, why does light do this? There's two reasons which I think don't fully explain it without, I guess, quantum theory, but these are the two reasons, and I hate one of them. The first reason that people love to say is that, well, if you imagine light like a car, right, and you imagine if this was pavement and this was mud, then if you let's say or I guess this is mud and this is pavement, right? Mud is harder for the car to go through. It's a little bit slower. The car's going to travel. So if you have the car wheels right here and right here, as right as it's about to enter, I guess that drawing doesn't really help. But if you had something like this, right, and this is the car, and this is like the chassis of the car, whatever, you can see 2 of the tires is in the pavement and 2 of the tires is in the mud. So if you imagine, like, these tires right here, they're going to be moving a lot slower, and these tires, now that they've been introduced into the pavement, they're going to move a lot faster. So you can imagine it's going to kind of, like, if this is moving faster, it's kind of swivel the car over and bend it to a new trajectory. I genuinely hate that explanation. It's good for, like, I guess, remembering, like, if you want to visualize, like, okay, light is entering a slower medium, which way is it going to bend? I guess you can think about it like this, but I don't think this explains what's going on. Maybe light does operate like cars, I don't know, but the explanation that I like a little bit better is something called Fermat's principle. And what Fermat's principle tells us is that light will always take the path of shortest time. So If you think about like this distance, right? Light won't really travel like this. And like it won't not refract and just travel in a straight line. It's gonna bend. And if you think about it, that kind of makes sense because light is moving slower over here. So it's spending a greater amount of distance and a greater amount of time in a material that's slower. So what light's going to do is for the material that is a little bit, for the material that's slower to travel through, it's going to take a shorter distance and then it's going to increase that distance once it reaches a material that's faster for it to move through, right? It's trying to minimize its time by spending less time in the material with the air. Now you might be asking, well, in that case, couldn't it just take this kind of path, right? Like where it goes straight down and then refract here. Well, now you've made the distance a lot larger, and it's this idea of you got to balance distance, right? Because if you make the distance really large, it's still going to take more time, and you got to balance like how much time you spend on each material. And the fact that light just knows that, and light just conforms to the Fermat's principle is kind of nuts, and I still don't understand why. But that's just, I guess, a more logical way to think about it that is, I think, more grounded in actual physics. So the question becomes, well, how do we figure out these angles, right? Like, if I know this angle, how can I figure out the angle of refraction based off the angle of, or the index of refractions, right? And that process, or the law that describes that, is Snell's law. And Snell's law tells us that if you take the index of refraction, index of refraction for the first material, multiply it by the sine of the angle of incidence, or the angle to the normal of your first material, right? That product is going to end up equaling the product of the index of refraction for the second material multiplied by the sine, or I guess the product of the index of refraction and sine of the angle of refraction. So, okay, hopefully I said everything right there. Sometimes I think faster than I speak. But this is Snell's law, and I should really put it too, because, it really depends, which way is what. So ones and twos, bit more clearer. So what this is pretty good, because what we can kind of do is we can say, well, N1 over N2 is equal to sine theta 2 over sine theta 1. So let's say we have air, right? Air is N1. If N1 is greater than N2, which for a vacuum it would just be 1, right? Because speed of light in a vacuum is going to equal speed in the light of a vacuum over 1. This is going to be greater than 1, so this ratio has to be greater than 1, and this means sine theta for the angle of refraction will be larger than the angle of incidence. And because of sine, if you think about the sine function, right, from 0 to pi over 2, right, sine increases with the angle. So if sine theta 2, or sine theta of the angle of refraction is greater than sine of the angle of incidence, then sine, the actual angle of refraction, is going to be greater than the actual angle of incidence. And if you're given numerical values, you can actually figure out one of the angles based off the other three. So that's Snell's law. It kind of describes more, it's kind of like Fermat's principle, but more specific. Fermat's principle says, well, light takes the path of least time. Snell's law says, well, this is the exact path light takes, depending on the indices of refraction. So yeah, hopefully this video was kind of helpful. I'll go over an example problem to kind of show you this law in action. And yeah, thank you for watching. Or should I say this? Hopefully this video is enlightening. Get it? Because we're dealing with light. You can see my reflection. How cool is that?